In our last breakdown, we built an event-driven ingestion tier using Apache Kafka to successfully buffer 10 million concurrent requests. But buffering data is only half the battle. Eventually, that data must be written to disk. If you dump a massive, high-velocity event stream into a single monolithic relational database, you will instantly hit a hard hardware limit. Disk I/O saturates, row-level locks cascade, and your entire persistence tier hits a fatal deadlock. To break this physical bottleneck, we must scale horizontally. We take our massive terabyte-scale monolithic database and partition the data across multiple independent database nodes. This is called horizontal sharding. Instead of one server handling 10 million writes, we distribute the load across a fleet of servers, ensuring that compute and storage capacity scale linearly with user demand. But how does the system know which shard holds which piece of data? We introduce a routing layer that utilizes a consistent sharding key. In a ride-sharing app, this is typically the user ID. When a write request arrives, the router passes the key through a hashing function and applies a modulo operator based on the total number of shards. This deterministic math ensures that all rides, payments, and ratings for a specific user always land on the exact same physical server, completely eliminating the need for expensive cross-node network joins. However, distributed data introduces a severe risk to data integrity. What happens if shard B loses power a millisecond before a critical transaction is written to the physical hard drive? To prevent catastrophic data loss and maintain strict ACID compliance, enterprise databases rely on a write-ahead log, or WAL. Before the database ever attempts to modify its internal memory tables or data files, it writes the raw transaction details to an append-only sequential log on the disk. Sequential disk I/O is exponentially faster than random access I/O. Once the transaction is appended to the WAL, the database acknowledges the success to the application. If the server experiences a catastrophic crash before updating its memory, the data is perfectly safe. Upon reboot, the database simply reads the write-ahead log from the exact point of failure, replays the transactions in sequential order, and rebuilds the memory state perfectly. Zero data loss. Maximum throughput. By combining event-driven message brokers, mathematical shard routing, and sequential write-ahead logs, you transform a fragile backend into a highly available, fault-tolerant system capable of planetary scale. If you want to master the architectural patterns that power the world's largest tech companies, hit subscribe, and I will see you in the next system design breakdown.